Good afternoon, David Eastwood, Geotech Engineering and Testing. How y'all doing? We're going to be talking about a geoforensic evaluation of a school building in Texas today. This is kind of like a one-story building, a little partially two-story, but mostly one story. And people are still joining here. The project timeline and then the project. We're going to be talking about the agenda, the project timeline, site visits, field explorations, laboratory tests, engineering analysis, reasons for foundation distress, repair techniques. We have about 120 people RSVP today. And if you have any questions, type it in the chat or Q&A here. I'll answer it. I work with Geotech Engineering and Testing. The firm has been around for about 40 years now. We do geotechnical, environmental, material testing, and we work all over Texas, Louisiana, New Mexico, Oklahoma, Arizona. We're licensed. And so forensics is about 5-10% of our work. So it's kind of interesting. We have about 60 people, and we have our own rigs, so we can mobilize on projects quickly. If you need to reach me, my email is de@geotecheng.com, de@geotecheng.com. My number is 713-699-4000. So just kind of if you need to reach me. This is the agenda. We kind of talked about it in a minute. Timeline. This project, they did the initial geotechnical work for it in 1979. They did the structural drawings in 1979, civil drawings 1979, and the construction completed in 1982. It's a nice elementary school. Did the survey and all that stuff there was another new boundary survey done in 2025, and we got involved in it because the school district came to us and said, hey, we have a lot of foundation problems, floor slab problems, a lot of cracks in our building. What's going on? And so we went out there and got involved September of 25, and we've done site visits many times during our investigation on this project. These are some of the pictures of the exterior of the building. Had cracks in the bricks, cracks in the concrete, a lot of separations in the joints out there. It's an expansion joint there. You can see the joints opening up. There was a helical piles. This school was repaired one time or twice, and they used helical piles, but they did partial underpinning, so it was not very effective what they did. And there was a large tree was taken out on this side of the school, kind of towards the north side of the building. That's where a large tree was taken out. Some of the columns in the building settled, caused a lot of cracking of the concrete. There was no joints between the isolation joints between the columns and the flat work, so there was a lot of cracking out there. And so that was kind of important. A lot of the flat work around the school were pretty flat and with negative drainage towards the walls. A lot of trees next to the building, oak trees and pine trees. A lot of cracks in the flat work, joints separating, sidewalks settling. See the joints. Water was just standing in some of the paving areas. bad drainage and stuff, no area drains. You go inside the building, you look at it. The floor slabs were sloping, and there were some bumps in the floor slabs. Now, we had floor slab covering, so we couldn't tell exactly what those bumps were. It could have been curling when they poured the concrete. We couldn't tell, but there were bumps there. And you could tell, where the bumps were. There were half an inch kind of separation in the slab from the high point to low point in a 4-foot uh, ruler there. So you can see that's a length of a bump. Again, we put a 4-foot level there, and we could see where we had carpet and where we had these bumps. Again, could have been curling. Floor slabs were not level. This is the kind of a length of a bump across the whole classroom. Again, it's another bump here. You can see half an inch out here, separation. Floor slab not level across the bump. Yep. You can see here the length of the bump here, about 28 feet. Again, you put the 4-foot level in here. You can see the separations from high point here. That's at various locations throughout the floor slab areas. See that over here. Here's about 27-foot length of the bump. Here's another bump here. Slab not being level across the 4-foot level. Length of the bump. We had column, sheetrock cracking. Some of the columns were moving. So we had cracks in the sheetrock where the joint was. Again, some more movements out there at the corners. Cracks over here. More sheetrock cracking throughout the school. This is kind of like the floor slabs. And you can see drill piers. In 1982, they built this thing. I think 79 did the geotechnical. They set the piers, 10-foot piers on this project. The floor slab was only 4.5 inches thick. So with number 3 bars at 16-inch spacing. These are 1854s, 18-inch shafts, 54-inch diameter bells, depth of 10 feet. The initial geotechnical report said piers at 10 feet. It's a drawing, initial drill piers, 10-foot piers. The exterior beams were supposed to be 24 inches. Field exploration, we did some GPRs here, concrete coring, drilling and sampling, tree survey, macro elevations, pier exposures, test pit excavations, and crack surveys. First thing was GPR went out there, and the GPR the building where we could access to, we had access for, and we also did coring. We cored at where we did interior borings here, and we did macro elevations of the school. We did 5 borings inside, and then we did 4 borings outside. And we also exposed the piers at 3 locations: test pit 1, test pit 2, and test pit 3. And then we exposed the exterior beams at 3 locations: at test pit 4, test pit 5. Let's see if I can find test pit 5. Here's test pit 5 and test pit 6. So we exposed the grade beams and also drilled PRC what was actually built. GPR uses basically an antenna, transmits electromagnetic energy like a cell phone, and is located within the antenna. It reflects the signal when it picks up the soils with different, they call it dielectric values, kind of like properties. We did, of course, GPR, where we did our concrete coring and borings. Also, we want to know if there was any kind of utilities out there. So we did both inside and outside the building, the GPRs. This thing looks like a lawnmower. You go in there and it's used mostly for, presence of voids, high moisture, underground utilities, where the steel is. It's kind of, you can use that GPR on the slab, and you can see here where the steel is. Here's our boring locations. These are where the steel is. The rebar, this boring B1, boring B2 inside, and you can see the boring. Let's see, boring B2. That's where the steel is. This is the boring location. This is boring B3. These are where the steel locations are. The rebars. The location, of course, we didn't want to do the borings and coring where there was no rebar. Okay. And you can see here the rebar locations. This is the boring location. That's the GPR again. Want to get through the floor slab areas everywhere. That's B5. It's the boring location, rebar locations. B6, that's in the parking lot. Rebar locations, this boring location. That's B6. We did it over here. That's where the rebar is. And here's the B7 right here. The rebars are here. B8. These are the rebars here. We did it in the middle, so there's no rebar. We did one in the grass. We made sure there was no utilities underneath it. That's B9. We cored the concrete inside and outside. The concrete was supposed to be 4.5 inches. In some areas was like 4 inch. Some areas was like 5 inch, 5.5 inches. Here's the 4 inch concrete core. 5 inch, 6 inch, 4.5 inch, 4.5 inch, 5 inch, 4 inch. We saw some voids underneath the concrete. The pad underneath the slab was like 2-3 feet thick, and the pad settled with time. I mean, the school was built in 1982, so it was, it's pretty old, school, 40, 50 years old. So, um, with time, some of these older structures, the pads will start settling and creating voids underneath the concrete slab, and the slab starts sagging and dropping. And you can see the void in the pad, separation between the concrete slab and the pad. Here's the void. And there were some areas that there was no void. We got our portable rig. It's a gasoline operated portable rig that we have. Can do borings up to 20 feet deep inside the building. This is our own rig. So we get out there and with our rig, do the borings, get soil samples all the way down. We extrude the samples, the soil samples, You can see the sandy clay soils that's coming out. We did have some fat clays too, gumbo clays, but mostly sandy clays. We measured the water level inside with the tape measure with the weight at the end of it. Threw it in the hole when it said plumb. It's where the water was, but we didn't find any water in any of the borings where we did, and no groundwater. We did borings outside with our truck rig. And the borings outside, I think, were 20, 25 foot deep. Stored the samples, measured the water levels, and we hit no water anywhere inside or outside, no groundwater. After we finished, of course, we kind of mixed the non-shrink grout, and we grouted the holes from bottom up. Make sure the holes are filled with concrete. We probe the holes, make sure none of them want to settle or have any problems. Everything was grouted. Oh, this was the building here. We had a lot of trees on the north side. Right here, the trees on the north side. A lot of them on the east side, and some trees on the south side. And if you look at the elevation data, for example, you see the east side of the building is settling. The edge is dropping. There are a bunch of pine trees here. So you can see the pine tree. In the parking lot, we have some oak trees as well. This is northeast of the building. This is southeast of the building. Southeast of the building, we had some oak trees and pine trees. Southeast of the building, near the building. This is south side of the building. South of the building. We did micro elevations to evaluate the relative elevations of the floor slabs using the Foundation Performance Association guidelines and also PTI, Post Engineering Institute. That's how we measure the water levels with the Stanley tool. And you can say the relative elevations of the floor slabs. We got actual elevations measurements here. It's kind of hard to see. But see the contours in here. Here's a better picture here. Shows the green stuff. That means it's settling. The darker the green is, means it's shrinking out here, settling. North is here. This is where a bunch of trees here. So the edge we're dropping over here. So here on the north side here, elevations were higher. You can see pretty lot of shrinkage here. Here, there's some heaving here, some settlement here. Here, the center of it's kind of heaving. So we also exposed the piers and test pits. We had for the piers, we used the test pits 1, 2, and 3. They were exposed piers, and test pits 4, 5, and 6. We checked the grade beams. The piers, we wanted to measure the depth of the drill piers, the shaft size, the bell size. For the grade beams, we wanted to measure the depth of the grade beams, their width, and compare all that to the design drawings. We started excavating at the locations around the building, various test pits. We exposed the drill piers. You can see the piers. Here we had good connections between the pier and the grade beams. That's where the pier is. That's test pit number 3. Here's shaft diameter of 16 inches. That's test pit number 1. Oh, see the drill shaft here? And we measure the rod to measure where the bell was. Right here. This is the drill shaft. Here's the bell, tip of the bell. And that's the beam of 24 inches. Test pit number 1. Measure the distance between the shaft and tip of the bell. Here's 13 inches. The bell is 42 inches in diameter. We found a gap between one of the piers at test pit number 1 and top of the grade beam. I think it was like an 8-inch gap right there between the top of the pier. I mean, just the pier was just sitting there, and the grade beams were not sitting on top of the piers. And here's the drill shaft right there. And you can see the test pit number 2, picture of the pier shaft. That's test pit number 2. Pier's depth was only 8 foot. The design was 10 foot. Grade beam was 24 inches. The diameter of the bell, this test pit number 2, was 32 inches. This is the pier. Here's where the edge of the bell is. There's a connection between the grade beams and the beam and at the pier. Solid connection at test pit number 2. Test pit number 3, shaft was 17.5 inches. That's the shaft, test pit number 3. The pier was 8.3 inches, 8.3 feet at test pit number 3. Again, the design was 10 feet. The grade beam thickness was 24 inches, test pit number 3. The bell was 32.5 inches. So it was undersized. The connections between the pier and the grade beam was good. Test pit excavation for exterior grade beams. We excavated exterior beams to see at various test pit number 4, 5, and 6 what was the beam thickness and the width. Here we measure the test pit number 4, test pit number 5, test pit number 5 here again, exterior beam, test pit number 6. That's test pit number 6. Beam depth, test pit number 4, 24 inches. Beam width is 9 inches. Design, I think, was 12 inches. That's test pit number 4. That's the bottom of the grade beam. You excavate, you go underneath it. That's what you get. That's the width of the excavation was 45 inches. Here the test pit was 37 inches. The depth was 58 inches with depth of the excavations. We found a piece of helical pile here at test pit number 4. I guess they tried to repair the foundation. That's a bracket for a helical pile. It's not engaged with the beam. There's a void here between the bracket and the beam here. This is test pit number 4, 5. You saw the beam depth of 24 inches. This is the bottom of the beam, and test bit number 5 was 12 inches wide. And again, the excavation was 40 inches, 34 inches, test bit number 5. Excavation was 46 inches, test bit number 5. The exterior beam was 12 inches. At test bit number 6, it should have been 24 inches. The grade beam width was 15 inches at test bit number 6. The excavation was about 39 inches. The width was 35 inches and the depth was 50 inches. Test bit number 6. We use hand penetrometer and we check the soils at the bottom of the grade beams. You see what kind of a strength it has. And backfill the area. After compaction, we use a jump and jack to compact everything. Backfill all the holes. And pour concrete where we excavated in the concrete. So test bit number 1, we had soils. Lean clay 0 to 14 inches, 14 to 36 inches, we had sand. Below that, he had lean clay. The pier was only 7 foot at test bit number 1. Bell size was 42 inches, design was 48 inches. The pier depth 7 feet, supposed to be in 10 feet. Shaft was 16 inches, that's okay. Exterior beams were 24 inches, that meets the design. Basically, there was no connections between the pier and the grade beam. There was a 8-inch void between the top of the pier and the exterior grade beam at test bit number 1. Test bit number 2, 0 to 48 inches was lean clay. 48 to 120 inches was lean clay. The pier depth was 8 feet. It should have been 10 feet. The bell is 32 inches. It was supposed to be 42 inches. Shafts was 16 inches. It was supposed to be 14 inches. The exterior beams were 24 inches. That's just fine. There was good connection between the exterior grade beam and the piers. Test bit number 3, from 0 to 12 inches was lean clay. From 12 to 112 inches was fat clay, gumbo clay. The pier was 8.3 feet deep, supposed to have been 10 foot deep. The bell was 32 inches, was supposed to be 48 inches. Shaft was 17.5 inches, supposed to be 16 inches. The exterior beam was only 12 inches, supposed to be 24 inches. And they had good connections between the pier and the exterior grade beam. This is test bit number 4. 0 to 2 inches, we had lean clay. 2 to 4 inches, we had sand. Below that, we had lean clay to 14 inches. 14 to 24 inches, we had sand. Below that, we had lean clay. And the grade beam was supposed to be 24 inches, which is 24 inches. The beam width was 9 inches, the design was 10 inches. That's test bit number 5. 0 to 46 inches was sandy lean clay. The exterior beam was 24 inches, which is fine. The width was 12 inches for the grade beam. Design was 10 inches. And test bit number 6, 0 to 50 inches was lean clay. We had exterior grade beam of 12 inches. The design was 24 inches, so it was all deficient. Remember, grade beam depth is a cubical function of moment of inertia. So when your beam is 12 inches thinner than it was supposed to be, that reduces the stiffness of the exterior grade beam significantly. The exterior beam width was 15 inches. The design was 10 inches. There was no water in there. Crack survey, we went throughout the whole building. We had a lot of crack on the east side where the trees were. We had cracks, and bumps all over the place. The crack width was, here was 0.035, and the length of it was 9 feet here. And just a whole table of the cracks and bumps. Here's a bump here. Width of the bump, 2 inches. Length of the bump was 9.8 inches. So there was a lot of cracks out there and a lot of bumps. We measured a lot of the crack sizes and the lengths of cracks. Measured the lengths, widths. A lot of hairline cracks. A lot of cracks, about 0.05 inches. Separations in the isolation joints. You can see separation in the joints here. Definitely, they didn't put enough control joints in the concrete, especially in the flat work. The crack here width 0.05 inches, 2.8 feet long. So there was a lot of cracks all over the place. We did laboratory testing, including the classification test, soil strength test, particle compaction test, particle size analysis, concrete compression test, the soil stratigraphy from the borings indicated we had concrete. Below that, we had fill. Below that, we had lean clay. In some areas, we had fat clays. Gumbo clays in some areas. In some areas, we had voids. So we had, about 6 inches of concrete, some areas. Then we had a little bit of voids, about 0.6 inches, 0.63 inches. Below that, we had lean clay. Below that, we had silty sand. Below that, silt. Below that, lean clay. In some areas, from 4 to 18 feet, we had fat gumbo clay. So we had very variable soil condition. So some areas PIs were 7 to 11. The sands had no PIs. The lean clays had PIs between 8 to 29. Fat clays had PIs between 38 to 33 to 38. The strengths were okay. These are typical boring logs here where we have 5.4 inches of concrete on boring B1. Below that, you have sandy lean clay to depth of 4 feet. Below that, we have sandy lean clay all the way down to 15 feet. This is an interior boring. It's boring B2. We have 4 inches of concrete. Below that, about 0.6 inches of void. Below we have silty sand. Below that, we have lean clay. And then we have a bunch of fill all the way down about 5 foot. So we had a lot of fill. PI in the lean clay was 11, 18. Boring B3, we had about 5.5 inches of concrete. Below that, 0.63 inches of void. Below that, you had silty sand. Below that, we had sandy lean clay. Below that, we had lean clay. PIs of 16, 10. B4, we had 6 inches of concrete paving. Below that, we had a couple of feet of silty sand. Below that, we had sandy lean clay. Below that, we have lean clay, PIs of 29 and 7. Us B5, we had 4.75 inches of concrete slab. Below that, we had 1/4 inch of void. Below that, we had silty sand. Below that, we had sandy lean clay. Below that, we have lean clay all the way down, 32 PI. At the bottom, we had some fat clay. B6, we had fat clay here below 8 feet. We had 4.5 inches of concrete. Below that, we had silt. Below that, we had lean clay with sand, fat clay. Here's another one, B7. We had concrete slab, 5.5 inches. Below that, we had sandy silt. Below that, we had lean clay. Below that, we had fat clay with a PI of like 38. Below that, we have lean clay all the way down to 25 foot. It's on like an exterior boring. This is parking lot. We had 4.5 inches of concrete paving. Again, the flat work was like 4.5 inches. Below that, we have sandy lean clay, PI 11. And then we had fat clay below that, below 4 foot. And then below that, we had lean clay. The strengths were okay. That's B9. We had exterior boring in the grass. We had sandy silt. Top 2 feet. Below that, we had lean clay. Below that, we had fat clay. Strong soil. We calculated the PVR with this site, and it was kind of average about 1.5 inches PVR. PVR kind of is a measure of how much heat you can expect on this site. So you have a potential vertical rise of 1.5 inches on this site. We ran a couple of Proctor tests to check the compaction underneath the floor slabs and paving areas. The soils were basically sandy lean clays with a PI of about 10. That's the Proctor curve. Got an optimum of about 14%, maximum dry density of 112. Here's another one here. Lean clay again, PI of 7. Dry density 117 and 10.7. We did some grain size analysis on this thing here. And we got number 200, and we can see more than 50% pass number 200 sieve, about 56%. So basically sandy lean clay. Concrete compression test. We took that concrete cores that we cored on the floor slabs, and we put them in a compression machine, and we broke up and see what kind of strength we get. And we got values of 3,000, 3,300, 5,900, 4,800. The spec called for 3,000 PSI, 28 days. So your concrete pass strength, it was good. We checked the aerial photos. We did engineering analysis, aerial photos, review of the topographic map. We looked at the macro elevations. We looked at the field compaction. We checked for water, perch water tables, soil moisture profile, and liquidity index. We checked the rainfall data, GPR data, slab thickness, strength of the concrete, crack survey, and pier depths. This is the site. That's what it looks like in 1944. There was nothing out there. 1978, it was like there was some earthwork was being done. 1995, that's when the school was already built. The 2002, 2006, you can see the school. 2011, 2015, 2017, 2021, 2025. Lots of residential developments around the property. It was flat. There was nothing out there. We look at the elevations on the basis of what the PTI, Post-Tensioning Institute, talks about, relative elevations of slab on ground foundations. Couple of definitions. Deformation is changing shape of the foundation from after original foundation construction. Deflection is a maximum deviation from a straight line between 2 points. And deflection ratio is deflection divided by horizontal distance over which the deflection occurs. If you want to look at the deflection between points 1, 2, and 3, this is the actual deflection, and this is not. This is the wrong deflection. So the actual deflection is smaller. Another concept called tilt is basically a tilt is a planar rotation measured over the length of the or width of a foundation. So tilt is y, the actual movement, over x, the horizontal distance. So the allowable tilt is about 1% by ASCE. So the actual deflection that on a slab that we can tolerate in general is L over 360. That's 1 inch in 30 feet. So your slab is not supposed to be out of level for more than 1 inch in 30 feet. And overall tilt limit is 1%. So we took 2 sections on the floor slabs elevations. Section AA, section BB. See what the floor slabs are doing. The black line is the floor slab elevation change. That's the distance from 0 all the way down to here. Distance in feet. And we calculated deflection ratios. We measured like at point number 1. Deflection number 1. Here, L over 918. Deflection 2 areas. L over 145. Elevation number 3 areas is L over 1220. Percent tilt was 0.06%, less than 1%. And all these things were smaller than L over 360, which was less than the allowable deflection. So the slab did not fail. Here's again the slab in second section BB. You can see a deflection of about 1/2 inch here. Almost 1 inch over a distance of from, I don't know, about 130 to about 180 feet in 50 feet, which is not very much. So deflection ratios were L over 778, L over 983, L over 1758, which is very small, all smaller than L over 360. Percent tilt was 0.07, which was less than 1%. The differential movement, section AA was 2.1 inches, section BB was 1.6 inches. That's 2.18 inches over 283 feet. The BB was differential movement over 181 feet, which is very small. Section AA, actual, movement that we explained, deflection ratio we measured was L over 918, less than L over 360, so it passes. Tilt was 0.06, less than 1%, passes. Section BB was L over 778, smaller than L over 360, it passes. The tilt was 0.07%, less than 1%, it passes. Compaction, we could not get a good sample of the soil under the floor slab because the soils were very sandy. It kind of fell apart. So we couldn't get good sample for checking compaction. Perch water table, we checked the boreholes in the floor slab areas. We didn't see any standing water, so there was no water under the floor slabs, no perched water. So moisture profile, we ran moisture tests on the soil sample. This is a really dry and wet condition moisture profile from PVR. And the soils were even smaller than that on the moisture. So the soils under the floor slabs were very dry. There was no sewer leak. There were no plumbing leak. That's boring B1, interior boring to a depth of 15 feet. The red area means the moisture profile. The red is the boring B2 moisture profile, a lot less than the dry and wet conditions. Soil extremely dry. Boring B3, interior borings. Soils were extremely dry. The red ones. Boring B4, interior boring. Soils were extremely dry. These are the wet and dry conditions. Dry condition and wet condition from PVR. This is boring B5. You can see the dry condition, the dry moisture condition, and the wet. This is exterior boring, B6. Soil was extremely dry. This is the dry condition and this is the wet condition. B7, the profile moisture was dry. This is the dry conditions from PVR, and this is the wet condition from PVR. Boring B8 was kind of like average near the top 10 feet, then became dry. And of course, boring B9 was totally dry. That's exterior boring. And this is the dry moisture conditions, the wet moisture conditions from PVR. We'll also check the liquidity index. Basically, liquidity index, want to know how far the natural moisture natural moisture content is between the liquid and plastic limit. Liquidity index is moisture content minus plastic limit divided by liquid limit minus plastic limit. It's just a relative moisture condition of the soil. If the liquidity index below 0, that means the soils are dry. It's above 0, it means the soils are wet. Majority of all the borings in the interior of the building and the exterior of the building show dry condition. This is the exterior borings showing liquidity index negative. That means it's dry. These are the liquidity index for interior borings and show it's all negative. That means the soils were dry. Rainfall data. We looked at the rainfall data during the construction of the building. In 1982, we had about 40 inches of rain. In 1981, we had 46 inches. In 83, we had 45 inches. Overall, those years, the rainfall was a little less than what the average rainfall of 50 inches that we have. So the soils were dry when they were building this school. When they took out the tree out there on the side of the building in 2017, we had rainfalls of 56 inches, 54 inches, and 76 inches. That means the soils were very wet at the time the tree was taken out. That area was dry. So this indicates that potentially where the tree was taken out on the north side caused some heave because the tree was taken out and the soil wanted to rehydrate. So we also look at the GPR values, and this is where we did the borings in here. That's where the steel was. Around the GPR, near the top in here. The red lines indicates 1 to 2 feet below grade conduits here. Also, the GPR showed the slab was 5 inches thick. The rebars were 1 to 2 inches below top of the concrete. The spacing of rebar was 16 by 16 inches. The specs calls for a slab 4.5 inches. The GPR said 5 inches. The steel 16 by 16. GPR says 16 by 16. Here's boring B2. Design the slab was 4.5 inches. Steel spacing 16 by 16. GPR says 5-inch slab, 1 to 2 inches of concrete cover. The steel 16 by 16. Red line indicates conduits. This is boring B3. Says a slab 5 inches, 1 to 2 inches of cover. Steel 16 by 16. Blue lines indicates saturation. High moisture saturation in these areas. That's boring B4. Same things. Shows red line indicates conduit. These are some conduits here. The steel was 16 by 16, slab 5 inches. This is boring B5. The same thing, just 5-inch slab. Cover at 1 to 2 inches, 16 by 16 steel. That's boring B6. Red line indicates conduits 1 to 2 foot deep. It's a conduit near the boring. B7, here's the conduit. B8, here's the conduit. B9, conduit right next to it in the grass. We did the borings. The conduit is outside. This is in a flat work area. So when we look at the whole thing, the red marks here, they're kind of like potential voids in these areas in the floor slabs. The blue areas indicate the areas of saturation. These are all concrete. The slab thickness. The design was slab was 4.5 inches. And we measured slab thicknesses anywhere from 4 to 6 inches. ACI 117 says slab should not be thinner than 0.25 inches or thicker than 3/8 of an inch from the design. But in this case, we found areas that were thicker and areas that were thinner. So in general, the slab thickness did not meet ACI 117 specs. The concrete slab strength, we did the compression test on the concrete. The concrete met specifications. You had adequate strengths. 3,000, 5,000, 900, and 4,800 PSI. So the concrete was good. So the design was, of course, 3,000. Cracks, we found a bunch of cracks all over the place and bumps, mostly on the east side of the building. Drill piers. We ran a software by F.PTI, Foundation Performance Association, considering the soils that we have on that site and the loading, and assumed a pier loading of 20 kips. And we calculated the piers should have been 16 feet deep to resist uplift due to expansive soils. Okay, so, but they designed the piers for 10 foot on this project. So we say that the 10-foot piers were not deep enough. This is the software from F.PTI. You put the load on it. You put this unsaturated soil mechanic data in there in terms of the depths, the gamma values, the moisture, liquid and PIs, and you run it for uplift capacity and also compressive capacity. And we came up with a number of 16 feet for the pier depth. Reason for foundation distress. Inadequate design. Well, the designer said the pier should have been 10 feet. It should have been 16 feet. Improper construction. Well, we had places over there that the piers were only 8 foot or 7 foot deep. The design was 10 foot. We had grade beams that were 12 inches thick, supposed to have been 24 inches. The grade beams in areas were like 8 inches wide. Well, they're supposed to be 10 inches wide. So we had construction problems. Poor foundation maintenance. So here's we talked about the pier depths of 10 foot, and we measured stuff a lot less than that. And of course, the design should have been 16-foot piers. Improper construction, the slab thickness varied all over the place. It didn't meet ACI 117 slab thickness requirements. Piers were shallow, grade beams were smaller, the bells were small, so the construction was totally faulty. You had shallow piers, undersized bells. That's a problem. Poor maintenance. We had all kinds of trees around the building. These trees suck moisture and cause edge settlement on the slabs and the flat work. Flat work was kind of dishing and all that because of the tree roots. So there were trees everywhere. This is a UT, University of Texas at Arlington Research. If you got a tree and this is the distance from a tree from a building, that's the future height of the tree at D over H of 1. You can expect as much as 2.4 inches of shrinkage at the edge of the building. And trees affect foundations equal to twice their height. Here at DH over 2.0, you can have as much as 0.15 foot of shrinkage of the tree. So it's real crucial to put the trees, if you can, twice the height of the tree away from the building. Also, we had bad drainage around the building. If you go look at the pictures, we had some areas the water was just standing in flat areas. So in summary, we had insufficient pier designs. Pier supposed to be 16 feet. It was only 10 foot. The pier bell sizes were undersized. The shafts, there were separations, voids, all construction defect. We had large tree causing settlements. That's a maintenance issue. We had negative drainage. That's a maintenance issue. In terms of repairs, we told them, well, let's meet with your structural engineers and discuss our findings and come up with the repair techniques. In general, we gave them 2 levels of repair. One were relatively cheap, one more expensive. If they're going to keep the trees, we recommended to put root barriers out there to a depth of 6 feet. Alternatively, any trees within 40 feet of the foundation should have been cut. They decided to cut the trees and put some great myrtles in there. So all those big trees are going to be coming down. These are root barriers. You put the trees in a root barrier. Root systems grow downward, not laterally. The root barriers, you put them right next to the foundation, all the way down. In this case, we recommended 6-foot root barriers. And they're using like a 1.5 mil, 15 mil vapor barrier. Ideal depth of course, moisture root barrier is about 0 movement line. That's a line above which there's movement, below which there's no movement in soils. And if you got paving out there and you got exterior beams and stuff, again, here just the city of Houston requirements. They're talking about putting root barriers down, somewhere about 25, 26 inches, 28 inches. Just depending, but this is a sidewalk. This is a curb and gutter. This is your paving. And they recommend 28 inches, but for sidewalks, they recommend 16 inches. I recommend deeper than that. That's where the trees are. This is your sidewalk. This is your paving roadway. These are your trees. Sidewalks, they say 16-inch root barrier. And the roadway, they're talking about 28-inch root barrier. Bio barriers, another system. They got herbicide pills. The roots hit them and it stuns them. You can put them vertical or horizontal. That's a horizontal root barrier. It's a vertical root barrier. Doesn't let the roots extend out. It's a vertical root barrier. It's kind of how you install it. We also told them to provide positive drainage away from the building. You know, sidewalks should have 2% drainage away from the building. We also told them to do in the areas of the floor slab that were sagging, use polyurethane injection to level it and grind down the areas where they have bumps. The areas where they had bumps, we told them to grind them down, make the slab flat. The areas that were sagging, we talk about using polyurethane injection under the floor slab to lift it up. This is a kind of a truck. It's got 2 chemicals in it. They inject them in the floor slab areas. And as they do it, the floor slab will come up. These are the holes, you know, about 1/4 of an inch to a 3/8 of an inch. You put them every 2-foot spacing. You mix the chemicals and you inject it. The floor slab starts coming up. It doesn't change the soil characteristics. If the soil moves, your foam will also move as well. If the soil moisture content changes, the slab will move. Is basically if the soil moves, it moves. Moisture conditions from storm sewers and pipes on the slab causes slab movements. Trees will cause the slab movements. Moisture changes cause slab movements. Failure to control the foam injected cause bulging, cracking of concrete slab. Prior to hardening, water from the overlay wet foam can seep into expansive soils and cause a little bit of movement. High pressure can cause damage or blowouts. If underground utilities are located, foam can get in there and block them and plug the lines. There's a video of it. They go out there injecting it. You see the concrete is coming up. That's a polyurethane injection. Some of the foam comes out through the cracks. You're going to have to take them out. That's how it works. We also told them that if the areas that, especially in the areas where you have columns and, walls, we can underpin them, use the steel pipe piles to level them. You can do tunneling underneath the floor slabs and put these pipes about 20 feet deep. And this is what they look like. They're steel, like about 2 inches in diameter. You put them in segments. You screw them together and you push them down. And it does lift the slab up. You put them underneath the grade beams. It closes up the cracks. That's the bracket that goes underneath the grade beams. The good thing about steel pipe is you can do tunneling. Here's a house that they're using steel pipe pile on it. They put jacks all over the place. You measure the pressures in all at one location and do the lift all together. Otherwise, you're going to get cracking in the floor slabs. So the whole slab needs to be moving at the same time. You put a segment in there. You put a jack on top of it. You push it against the grade beams. You take it out. You put another steel pipe in there. Put a jack on top of it. Push it against the beam. Go to a depth of 20 feet. Uh, Basically, as a small surface area on these steel pipes and piles, and expansive soils cannot pick them up easy. They're easy to install. You can do tunneling underneath. It's kind of expensive. Push to refusal. Shallow pipe move up and down if it's shallow, up and down if it changes moisture occurs. If not pushed to the correct angle, the pipe may lay over and bend. Uh, if the pipe is overloaded, it can cause the pipe to bend. Improper moisture close to the pile, such as poor drainage, leaking, can cause the pier to move. But if you put it at 20 feet, you don't have to worry about it. Structural problems are not conducive to steel pipe. For example, if there is sufficient steel in the beam slab, they're not tough enough to be able to resist driving the pile. Sometimes you add a steel beam out there and you jack up your slab against the steel beam. If the contractor did not clamp the bracket immediately after driving the piles, the piling will spring back. And drought can cause loss of skin friction on shallow piles. A lot of problems can be mitigated by placing a sleeve over the pipe within the top 10 feet. Some areas where you got expansive soils, you put a sleeve around the pipe, allow the sleeve to move up and down, and the pipe does not move up and down. That's if you have expansive soils. If you don't have expansive soils like here, you don't need it. Tunneling. For you to install some of these piles, you got to do tunnel underneath the floor slabs. These tunnels are usually 3.5 feet by 3.5 feet, or 4 foot by 4 foot. You go in there and you dig a hole. You start putting your jack here and push the pile in the ground. That's the jack. If you don't have a beam, you add this steel beam in there and you jack against the steel beam your slab, okay? You don't jack against the 4.5-inch concrete slab. It will crack it. You have to add the beam in there. Comments? Despite our recommendations, some movement can occur. We recommend, of course, meeting with a structural engineer and conduct a leak test and review the plans and specs, write specifications for the repair techniques. Questions?